So 7.1 is exploring quadratic relations. In these notes, we're going to talk about quadratic functions, which will take the shape of a parabola, and we're going to learn the characteristics of what those types of functions look like when we graph them and what they look like in equation form. So our first blank, a quadratic function is a function of degree 2, so we'll fill that in. A quadratic function is a function of degree 2, just meaning that the highest exponent on any variable in that equation that you see will be 2. The equation of a quadratic function can be written in the form of y equals a times x squared plus b times x plus c, where a, b, and c are all constants and a cannot equal 0. So some examples of what that might look like: y equals x squared, the function on n, where n squared minus 4, so our highest degree is still 2, and y equals 3x squared minus 4x minus 7. So in that one we have two variables, but still the highest degree, the highest exponent on one of those variables is still 2. The graph of every quadratic function is called a parabola. Oh, my highlighter's on. Parabola. And a few examples of what that might look like is below here. So these are some pictures of what parabolas would look like, and I'm going to label some important parts that we're going to talk about throughout the rest of this section. So if we go through the properties first, and we'll label those things on our graphs as we talk through them. So properties of parabola: the vertex is the maximum or the minimum point on the graph. So identifying where that is on these two, this first parabola would have a max value right here, and this parabola would have a minimum value right here. Minimum because the rest of the graph opens up, maximum on this first one because the rest of the graph opens down. So our vertex would be labeled if we just our x comma y. So our x value is 1 and our y is 1, 2, 3. So our vertex is at 1 and 3. In the second graph, our vertex is at negative 2, x, and 0 for y. The second property of parabolas is y-intercepts, so where the graph crosses the y-axis and your x value would be 0. So in our first graph, maybe change colors, our y-intercept here, crossing the y-axis where my x value is 0. So my y-intercept is at 2 and 0. Sorry, 0 and 2 because our x value is 0. And our y-intercept in the second graph, where it crosses the y-axis, is at 0 and when y is 1. Our third property, so we talked about y-intercept, is just our x-intercept. So same thing where the graph crosses your x-axis now and your y value would be 0. So we have 2 in this first one, right here and here. Those are our x-intercepts, and there's a way to solve for those if they're not on exact points, since we're going to learn how to find those. And our x-intercept on the second graph is also our vertex. So not only is that our vertex, that's also our x-intercept. They share the same point because our y value is 0, and it crosses the x-axis. Our fourth property, axis of symmetry. So the line about which the parabola is reflected. So it goes exactly directly through your vertex. And if the vertex is located at a point m and n, then it's always going to be just your x value, whatever m is or whatever x is if you know your vertex. That's your equation of your axis of symmetry. So identifying that here, our first graph, if I were to draw a line right through this point, my graph would be reflected or mirrored on both sides. It's symmetrical. So we know our vertex is 1 and 3. So our equation of our axis of symmetry is just x equals 1. In our second graph, if I cut all the way through my vertex, it'll be symmetrical on both sides. And we know our vertex is negative 2 and 0. So our equation of our axis of symmetry is that x equals negative 2. Whatever your x value is of your vertex is your equation of your axis of symmetry. Domain, the set of valid x values for the graph. So that's, if we were to look at this entire graph, the whole thing, it's going to be continuous for our x values. So we say x is an element of the real numbers. It covers everything. So domain, we have no restrictions on our x value. It's forever continuing down or up in both cases, left and right. So we say our domain is x is an element of the real numbers, just like we talked about when we were shading our solution regions in our chapter 6. And this one is also x is an element of the real numbers. Until we are told there's a restriction, our parabolas will always be x is an element of real numbers. And our last property is range, a set of valid y values for this graph. So with y's, we always have a max or a min, so there's always a restriction. It's not always y-er. So in this case, we look at our max value, which we said is 3 at our vertex. This graph does not exceed a higher value than when y is 3. So for our range, y is less than or equal to 3 on this graph. The rest of the graph is lower and equal to 3 for our y values. And in our second graph, it opens up, so there's a minimum point, so our graph is going to be greater than or equal to, and our y value is 0. Example 1. Graph the following quadratic functions on the same grid here to the right. So this table here, that you'll see my t table with an x and y, is just our table of values, where we're going to be plugging in x values into each equation to see what y value we would get at that exact point. So it doesn't matter what points you're picking for your x's, so I'm just going to pick a few, -4, let's say -1, 0, 1, 3. How about, so you want some positives and some negatives, as you know you'll have some on both when the graph is a parabola. Now we want to plug in -4 into this first equation to see what y value we'll get. So -4 squared is going to be 16, plus 2 times -4 will be a -8, minus 3. So 16 minus 3 minus 8 is going to be 5. 16 minus 11 is 5. So our y value is 5 when our x value is -4. Same equation, but our -1 now. -1 squared is 1, plus 2 times -1 is -2, minus 3 will give us a -4. When 0 goes in for x, so wherever there's an x, it's now just 0. 0 plus 2 times 0 is still 0, so it'll be minus 3. When we plug in a 1, 1 squared is 1, plus 2 times 1 is 2, minus 3. 3 minus 3 is 0. And plugging in our 3 to that equation, 3 squared is 9, plus 2 times 3 is 6, minus 3 will be 12. So those are the points we want to plot on this graph. -4 and 5. -1 and -4. 0 and -3. 1 and 0. And 3 and 12. Which will be up here. So you can see the shape. We know it's going to look like a parabola. So even though we don't have all the points, we can still connect those points. And it's continuous going up forever. So add those arrows onto the end of your rays. Now I'm going to erase this table of values for new points for B. Again, you can keep the same ones, -1, 0, 1, 3 throughout, or you can be picking new numbers, which we might here and there, just to show that it doesn't matter what points you pick for x. You just have to identify what your y value will be at that point. So here, y equals -2 times -1 squared. So remember, the squared is applied to your x value. Any negative squared is a positive. So it's really -2 times 1, which is -2, plus 2 times -1 is -2, minus 3 will give us a -7. Plugging in a 0 wherever you have an x again, that whole group will now be 0, so we're left with a -3. When we plug in 1s, -2 times 1 squared is -2, plus 2 is 0, minus 3, we're left with a -3. And when we plug in a 3, 3 squared is 9 times negative 2 is negative 18. Plus 2 times 3 is 6. Minus 3, we get negative 15. So again, we'll plot those points onto our graph, negative 1 and negative 7. 0 and negative 3. 1 and negative 3. And 3 and negative 15, which will go past where we can see, so we'll just say the lowest point there. It's going to be narrow and opening down. New table of values for C. Say negative 2, 0, 2, 4. How about? So y equals negative 2 squared is 4 times negative 1/2 will be negative 2. Plus 2 times negative 2 is negative 4. Minus 3 gives us a negative 9. When we plug in zeros for our x's again, those groups where the x is attached to is 0, so we're left with the negative 3. Plugging in a 2, 2 squared is 4 times negative 1/2 is negative 2. Plus 4 minus 3 is negative 1. And when we plug in a 4, 4 squared is 16 times negative 2 is negative 8. Negative 1/2, sorry, is negative 8. Plus 2 times 4 is 8. Minus 3, so the 8's cancel, and we're left with negative 3. So we just need to plot those points, and we'll do some comparison. So negative 2 and negative 9. 0 and negative 3. 2 and negative 1. 4 and negative 3. So we just have some questions to answer now. So the value of a changed. So what that was our coefficient that was in front of our x value. Nothing else changed. We always had a plus 2x minus 3 at the end of all of our equations. Those b and c values never changed, but our a values did. In this first one we had it 1, negative 2, negative 1/2. So we want to identify what effect did that have on our graph. How did those graphs change when we changed our a value? So we can see the thickness definitely changed. Some are wider than others. And the direction of the opening changed. Some opened up, some opened down. And the ones that opened down both started with negative a value. And the green graph that opened up was a positive value. So we can say the thickness of the parabola changed and the direction of the opening. So this sentence wasn't quite typed right, my apologies. So what does the value of a have? The parabola should have said, what does the value of a tell you about the parabola? So the direction of the opening. And we can say if it's positive, it's going to be opening up. And if it's negative, it means it'll open down. The thickness it also determines. So the larger the value, so if the value is greater than 1, let's say, if a is greater than 1, it's going to be thinner. The larger the number, the thinner it gets, the more narrow. And if a is a fraction or less than 1, if a is less than 1, but still greater than 0, let's write that in a double inequality, 0, a, 1, then our graph will be wider.